I thank you very much for the invitation and also for this nice introduction. And listening to the talk, I just have some difficulty that I'm also an organizer of an international workshop, which is now taking place this week. So I gave some talk in the morning, and I'm going to present you this talk. And so there were some technical difficulties to manage, but now everything is solved. So listening to the talks which I had yesterday and today, I see that my topic will be a little bit different. That I put more emphasis on the method developments and to show that how far we can push this new methodology, but I put less emphasis on applications. So I hope that at least I can manage to convince you and show these new method development directions, but there will be less on applications. But let's see that how far we can get. So the only extension I made with respect to the original title, that I ended this phrase that hybrid CPU, GPU-based HPC architectures, which means that I also include a couple of slides on recent developments on pushing these methods to high-performance computing and see that how far we can go and what is hopefully possible in the future. So what we are interested always is this strong correlation. So when you have electrons and when the electrons start to interact with each other, then they also generate kind of correlations between them. So you end up with new phases in matter, and that's this really due to the interactions between the electrons. And whenever you have very strong interactions, you have completely new phenomena. As one is in topological phases, or there's some high temperature superconductors. And especially nowadays, that's very hot topic. Also, the singular molecular magnets, where again correlations lead to new phenomena. What we also spend a lot is to describing, for example, the nitrogen fixation. This FEMO code is iron molybdenum cofactors and all these things. So these are very big complex systems, and they include the iron or other transition metals. So this is basically transition metal chemistry. Because whenever you have these transition metals, you have these strong correlations in quantum chemistry. This is one that is called multi-reference problem. So most of the methods available in quantum chemistry, like coupled cluster and DFT, they work very well at equilibrium position and for ground states and for single reference problems. But whenever you have degenerate states in the eigenvalue spectrum, in the energy spectrum, then there are a lot of problems, and mathematically these are not well defined. So this is basically the major area where we would like to present new alternative approaches, and hopefully that I can convince you that this is some directions also for the future. So I know that listening to the previous talks, this slide is again already something that might be different from the previous ones, but here just briefly, this is the so-called, which we call Hamiltonian, which describes the interactions between the electrons. So just we have some molecular orbitals which are labeled by this I and J, and you have some electrons which like to hop from orbital A to orbital B, or from orbital I to J with some spin. And that's this first term, and this T is the amplitude which describes the electron hopping. And the electrons also interact with each other, and this is the two electron interactions. So these pairwise interactions, this is the one that's mathematically written, this C dagger, CC, this second term in this so-called Hamiltonian. Now, if you have this general form, here just briefly mentioning that this is everything up to these two particle interactions. So this is not related only to quantum chemistry, but we use exactly the same formalism in condensed matter physics, nuclear physics. So there are extensions to also for relativistics, so where you have not just the spatial spin orbitals, but you have spinors, which means the Dirac solution. So whenever you have heavy elements, and then when the electron motions cannot be treated properly without including the relativistic facts, then you have to include that as well. And that's basically this Lenzedin and Actedin chemistry. And there are many other extensions. Just keep it in mind that when you put some electrons into some orbitals, this is what is called this CAS size. So what is this active space size? And the exact diagonalization is possible only up to 18 electrons on 18 orbitals. And now with these new techniques, we are in the range of 70 or even larger. You can do also finite temperature, time evolution, dynamics. You have access to these reduced density matrices. And from these, you can calculate all the different quantities like magnetization, order parameters, and transition matrix elements, and various other things. And then, of course, the big issue is now taking advantage of, besides the mathematical developments, all the developments from the IT technology, which is basically high-performance supercomputing. So briefly, that when you have a 8 orbitals, for example, and then you put the electrons on these 8 orbitals so that you have some sigma, pi, and so on, you would like to distribute the electrons, and this means that unlike in classical physics, in quantum physics, you have to take all possible combinations, you have to sum them up, and this U, that's what we call a tensor, which has as many legs, as many orbitals one has, and then if you make this linear combination of all the components, this is basically your wave function. So all the calculations that has been presented also in the previous talks, then all these depends on some kind of method. That can be DFT, that can be couple cluster, or now we talk about this tensor network state method. So by the way, there are these density matrix related methods, and there are these wave function related methods, and I will talk about these wave function related methods. The problem is that the size of this tensor scales exponentially. So basically, after 18 orbitals, we are dead because we cannot treat it with even with the most modern computers because of the exponential scaling. So we need some data sparse compressed representation of the wave function in some other format. And that's something, what is this called, DMRG or tensor network state, or it's also called matrix product state. So this big tensor, which has as many legs, like 1 to 8, this can be written and factorized in terms of product of matrices. So this A1, A2, A3, these are matrices. And so for each molecular orbital, we assign a matrix, and we can write down the wave function, this tensor U, as a product of matrices. And the big question is that how to get the optimal structure of these matrices and how to obtain the so-called matrix sizes, because the matrix sizes are the ones which finally determines the computational complexity, plus how big systems we can study and how complicated chemical reactions we can access in the future. Okay, the other thing is that this is then combined with some other methods also from the past, that this is the so-called rush. So which means that we have this restricted active space, that we take our molecular orbitals and we keep some in the so-called K space, which are this complete active space, so that we allow all electronic excitations within that subspace. And then we treat the others, which are less important but still important, up to some approximation. And this is what is called a restricted active space procedure. And this restricted active space procedure also has a long history in quantum chemistry, but it was not possible to apply it to large systems because of all the limitations. But combination of these ideas with this modern tensor network state, like with DMRG, that opened a new field and a new applications. And I will show you that how it is done. So the basic concept is that you take the most important molecular orbitals, which are the most important in some chemical reactions or most important in terms of electronic correlations. You put them into this so-called complete active space labeled by phi A in these cartoons on the left side, and then the rest you just allow only up to 2 electrons to be excited to all the higher lying energy levels, and we would like to get all the correlations from these. So there is a technical solutions for this, which the basis I worked out almost 20 years ago, but now there are nice extensions of this, and that's something that before I go to the details, I would like to show you that so that we have this CAS and the so-called rush, and there are these different terms in mathematics that how the electrons are correlated and within one block, how they are correlated in the other block, and then what is the correlations between one block and the other block. And so first of all, that when you just simply do the calculations, taking some larger bases like CC, PBTZ, for example, the carbon dimer, which we know it's strongly correlated or multi-reference problems, maybe on 58 orbitals K space. And here I listed the conventional methods that what you can obtain in the ground state energy. And then in quantum chemistry, usually the CCSDT parenthesis T is the so-called golden standard, because this is what people usually use to get results in the fastest way. And now I show you our results, which we call this rush DMRG, and with some model parameters which describes the accuracy settings. And so this is already below CCSDT. So just there was a recent paper where we demonstrated that this method has the possibility to outperform all the conventional methods that has been developed in quantum chemistry in the past. And because it treats all these correlations and all the correlation effects in a completely different background and framework. Now, if we stretch a molecule then I don't want to show you and overload you with millions of data, but you can determine the whole potential energy surface. And again, the accuracy is extremely stable, even in the stretched geometries. And you know that, for example, if you have a nitrogen dimer and then if you stretch it, then usually a couple cluster breaks down after a given bond length, because the problem gets so-called multi-reference, so that these methods are not suitable for such a strongly correlated multi-reference cases. But this method, this tensor network state method, together with restricted active space procedure, is fully stable. So we can reproduce spectroscopic constants and also compare it to other methods, which, for example, full CI quantum Monte Carlo developed by other groups, full agreement up to 3-4 digits and so on. So this was just first the demonstration that this method works, and then we also studied excited states and showed that even for excited states for the full spectrum, this is a very stable, robust method. There is no need to do anything prior. It's really a black box method and outperforms all the CC and other methods in this regime. Technically, there is just a cartoon that how to monitor the performance of this new method. That's shown on the top with red dots. That's the energy difference to some reference energy. That's the best one, like CCSDT. And then there are also with the dashed lines some other methods that you can use, like CI expansions or perturbation series in FPT2, and also the CCSDT as a reference. And you can see that DMR Girard gets to this CCSDT. And then it is extremely fast and accurate, and also it's in the same speed, and therefore you can really apply this without any prior knowledge or settings in your application. Now, as I said, that I didn't know what kind of talk I should give, so I put a little bit more emphasis on the mathematical aspects of this method. So maybe I will keep it brief. But what you can see on the top is that you take this so-called CAS space where you put all the important orbitals, and then this RAS space, which is less important, but still there are many small contributions which add up to finally a significant contribution. And you would like to write down this kind of splitting in this mathematical framework. And the idea is that you take the interactions within the CAS space labeled by H0 or H0, and the interactions between them as H prime. So the idea is that what you would like to have that you would like to increase the CAS space, which is labeled by L, taking larger and larger CAS sizes. And if you do this, then this H prime, the interactions between the CAS and RAS, should decrease. So at the very extreme limit, where all the orbitals in the CAS space, one simply recovers the full CI solution. Now, the big question is that how this method scales with L, because if we can do something for 8 orbitals and we don't have to do the same calculations that you would have to do for 50 or 100, just do it for 8, 10, 15, and so on. Of course, that's a tremendous amount of saving in CPU time and also in real time. So what's going to be the analysis in the next slide is that how this error that is measured simply by CAS space and by this RAS space with respect to some reference energy, okay? And I skip this because that's really mathematical. And as I said, listening to the previous talks, I think this is not really what people might be interested in at the moment, but let's show that the result that with the red one, we show that if you have this mathematical framework, you can generate data sets for this so-called RAS, so there's this restricted active space solution. You can also have the data points just for the complete active space solution. And with these data points, just put it on some scaling equation, you recover very nice lines. So here are some examples for smaller CAS spaces like the CH2, the F2 molecule, or the N2 nitrogen dimer, and for the carbon dimer. So what happens here is, as you can see, there are these CAS and RAS errors in the X and Y axis. And these data points, the numbers 4, 6, and I don't know, 8, 14 so far, labels this CAS size, so that how big was this L in the previous series. And you can see that as you systematically increase it, there's a straight line on a logarithmic scale. So one can use this new mathematical approach to really extrapolate also the full CI accuracy wave function up to some error, and this error margin should be something like this chemical accuracy, which is in the order of 10 to the minus 3. And in this little table, we just show that what would be if someone would just do the complete active space calculation, what would be the error how it decreases if someone does this restricted active space solution, and then how it's further decreased when one makes the extrapolation. And you can see order of magnitude can be gained from the cache to this rush X, which means this extrapolated rush. So this is very convincing and has a very rigorous mathematical framework behind the theory, and plus the numerical results also support it. Now, if you go to larger spaces like the chromium dimer for 16 orbitals, or you go to even a larger one like the carbon with 108 orbitals, and this is spatial orbitals, so with spin orbitals that would be 216 orbital space, then you also recover these very nice straight lines. And what is highlighted with red is that, for example, in case of this the chromium 2, we can outperform a couple of clusters, single, double, triple, quadruple. So it's a very expensive, high order calculations, very accurate calculation, but we can outperform it by 10 to the minus 3 accuracy with this limited Diamond-Rash calculation. And what is very important that our method is fully variational. So if you increase the parameters, you can get lower energy, but you can never go below the exact energy just by the Diamond-Rash, while this CC, the couple cluster, and all the other methods, they are non-variational, so there is no rigorous error control, while in these tensor network state methods, this is really the case. So what is nice is that one gets all this extremely well-defined mathematical framework together with the numerics. So I think this is going to be something that's what we push also recently for much larger and complicated systems. And one is this FEMOCO cofactor, which I mentioned in the introduction. It's a class space of 54 electrons on 54 orbitals. And even here, you recover these very nice straight lines. And here, this table works from other groups with different methods. And with our methods, we're able to reproduce all the previous results in very nice, accurate way. Plus, these methods now can be combined with high-performance supercomputing. So that's some 2 or 3 slides I just selected as the closing remark, is that what is nice that the mathematical framework is also scalable on modern high-performance computing. So here's something that if you also utilize GPUs, then together with the CPU and GPU parallelization, if you increase the GPU cards, then how the performance scales in terms of these matrix sizes, which are labeled by this D as a function of the GPU cards. And the dashed line shows you the theoretical maximum from NVIDIA. That would be 76 teraflops. And then we got more or less 72. So there is only a very little overhead on the calculations, and one gets this very nice, almost straight line scaling. And also, if you want to use the methods, of course, it's always a question about time and speed up. So in the speed up, it's again, we show that what is the speed up compared to a full parallelization on a CPU, where we had some 128 core CPU already. So it's already fully parallelized, but you switch to the GPU, you can still get a factor of 25, 30 speed up compared to the simple CPU case. So in the future, this really multi-CPU, multi-GPU solutions together with this extrapolation method and this Diamond-Rash, we think that it's going to be something that will be very widely daily used method in the near future. You can see this FEMOCO, which is 113 electrons on 76 orbitals. It's a very huge class space. It takes some 3.5 hours now in all these modern supercomputer technology. So as a concluding remark, what I just like to tell you that it's we are working on many things, and then so that people are using many different methods. Always the question that you do some kind of chemistry or some kind of physics, you apply some methods, but what is the error that you get? How you can rely on your results, whether the results really make sense in terms of physics and chemistry, or whether you inherit some kind of errors which propagate through all the calculations and which might affect also the conclusions that we draw from given calculations and simulations. And that's super important to have some methods which has a very rigorous mathematical scaling, what I just presented now. And it's together with these modern parallelizations like NVIDIA. There is this new DGX box which will come out in the autumn. And then if you combine MPI parallelization together with this GPU DGX, then hopefully in the long run, in the future, pushing calculations in the so-called exascale computation might be also possible. But and also simulation of realistic materials for much larger complex systems than what we have access now. And I thank you very much for your attention.